In the year 2020, we have images of black holes, breathtaking panoramas of the Milky Way, detailed snapshots of distant galaxies, and the stunning James Webb Telescope is getting ready for launch. However, 30 to 35 years ago, everything was so different that such news would likely have shocked engineers and scientists. If we had the opportunity to call a scientist directly in the year 1985 and ask a couple of interesting questions, like the existence of planets around other stars, they would probably say that it's likely, but not certain. Now, it's not 1985 anymore, and thanks to new methods and modern technology, today we have thousands of stars in our own galaxy that have their own solar systems. We have discovered planets of various sizes, characteristics, and masses at various distances from their stars. We have planets even larger than Jupiter that orbit stars in less than 48 hours, and NASA's Kepler mission has made a huge contribution to the search for such planets. It's no longer breaking news that Earth-like planets are being discovered. But let's reason more simply. As each of us has a specific idea of what intelligent life is, and each of us has an idea of the conditions under which this life can exist. Let's imagine a simple analogy: intelligent life in the universe and an ordinary tree. If I ask you whether a tree can grow inside an iron box, or whether it can exist there, you would accurately say no, because you understand that a tree requires certain ingredients, such as soil, fresh air, sunlight, and some nutrients. In fact, the logic is such that we just need to find the same things that exist on Earth, and then we will surely find life. This is how we think now. But consider the fact that you are not Mickey, defining the concept of life only like the one on our Earth, because you haven't seen any other life, heard nothing about it, and are unlikely to hear about it in the near future, and maybe never. So, if we set ourselves the question of searching or pondering whether intelligent life exists in the universe, it's important to understand correctly what form or type of life we want to find. It could be similar to us or something entirely different. Of course, the simplest ways to answer such a question are to apply mathematics, probability theory, and real observations. But in that case, once again, we will be looking for life solely similar to ours. Remember that tree I mentioned. The key point is that we know what it looks like and what conditions it needs. Therefore, we can easily predict where a tree can grow and where it's extremely impossible. If you want a simple answer to the question of whether life exists somewhere in the universe besides us, I will say that it's 100% likely, given what we consider as life. I know this is my personal opinion, but I will try to explain why I'm confident about it. I present to you 10 amazing places in the universe with a full potential for the formation of life. It's not a secret that soon after the formation of our planet, life appeared on Earth and is progressing today. Of course, it's possible that earthly life didn't originate on Earth, but came from somewhere else through natural cosmic processes. And in this conversation, it doesn't matter whether it originated here or somewhere else. What's important is that the basic ingredients for life exist everywhere we look. For example, consider a dozen places where these ingredients are most frequently found. First, there's gas ejected from young objects, like the Herbig-Haro objects, which contain various organic molecules. Another example is protoplanetary disks, where there's a vast diversity of complex compounds and organic molecules. For instance, there's the protoplanetary disk around the young star, H.L. Tauri, photographed by ALMA. The gap in the disk indicates the presence of new planets, and spectroscopic measurements reveal a large variety of carbon-containing compounds, which are essential for life. Even on Pluto, there's thallium and methane, and a rich organic haze. Even in the images from the New Horizons mission, atmospheric hazes are clearly visible and measured for the content of several carbon-containing compounds. Nebulae illuminated by a bright young star are rich in numerous complex carbon compounds, are reflective nebulae for containing a wide variety of complex organic molecules. Reflective nebulae are common sources of raw materials for life. By the way, inside meteorites, there are numerous amino acids and proteins, some of which are not found in nature on Earth. For example, the Murchison meteorite that fell in Australia in the 20th century. The fact that there are more than 80 unique types of amino acids suggests that basic ingredients for life, or even life itself, could have formed differently somewhere else in the universe, perhaps even on a planet that is not orbiting a sun-like star. The gas in the galactic center includes vital compounds. Idol's pharma is responsible for the recognizable aroma of raspberries, though Russian scientists don't acknowledge this. For example, the wave image of the galactic center shows us stars and gas, with a tremendous amount of material, including heavy elements and organic compounds, which are essential precursors for life. And this is the molecular cloud of Taurus, where new stars are formed. It contains dozens of organic substances, including carbon chains. For example, in the image, the brighter areas in red have the highest density and active star formation, while the blue areas correspond to cooler, less dense regions. However, organic molecules are found in both places. Planetary nebulae formed by the death of sun-like stars contain more than 20 molecular species, including fullerenes. These are abundant on Earth. Interestingly, fullerenes and complex organic compounds can form rapidly and survive to a significant extent during the evolution of any star. Nitrogen, hydrogen, and oxygen are strongly highlighted in this planetary nebula. Different colors clearly indicate the locations of various elements, which are separated from each other. Complex molecules, including fullerenes containing 60 carbon atoms each, have been detected in these planetary nebulae. And you don't have to go far. Sedimentary rocks on Mars contain rich organic compounds, some of which are over 3 billion years old. For example, the American NASA rover on Mars discovered ancient organic molecules embedded in sedimentary rock deposits that have existed for billions of years. They contain carbon and sulfur and could be associated with life beyond Earth. Over the past decades, our knowledge of the existence of planets around other stars has grown to incredible numbers. The number of known exoplanets has changed from a few dozen to more than 1,000 officially confirmed objects. Therefore, now we are confident that exoplanets can come in various sizes, be at different distances around all types of stars, have different masses and characteristics, and these are real data. It's not surprising that against the backdrop of such acquired knowledge, various questions arise in our minds, seemingly logical at first glance. For instance, when will we find the first inhabited planet beyond the solar system? Or what does habitability on a planet actually mean? Do planets exist that closely resemble our home, Earth? All this is done in order to understand where else life might exist. However, the thing is, the more we learn, the more we realize that being interested in and searching for a planet similar to ours with the presence of life is very inappropriate. This is because the universe is incredibly diverse, and places with the presence of life might not be anything like Earth. Perhaps these conditions could be even better or completely different from what we can imagine. We'll talk about why the assumption that a planet similar to Earth is a requirement for the existence of life is misleading. Having only one successful example, the planet we inhabit, leads to this kind of misconception. If we look at our solar system with all its planets and moons surrounding us, it becomes obvious that Earth is something unique. Only we know why we consider it special. Maybe it's because Earth is the known world where life originated, was sustained, developed, and flourished. It transformed the biosphere and eventually became complex, diverse, intelligent, and technologically advanced. Scientists are looking for conditions that resemble those Earth has experienced and continues to experience. They assume that a potentially habitable planet with life must be similar to Earth. But this is where they make a crucial mistake, because these assumptions imply that the conditions our Earth has faced are the most favorable for the desired outcome of life. However, as we learn more about the universe and the solar system, we have solid grounds to challenge such an assumption. There are 5 key points we need to consider. The first thing that comes to mind is a planet the size of Earth. After all, it seems like the ideal size for life. If we're too large, we might be enveloped in a massive hydrogen or helium envelope, like Neptune or Uranus. And if we're too small, we might struggle to maintain our atmosphere, like Mars or Mercury. Hence, the conclusion is that Earth's size is the way to life, right? Saturn's moon Titan is smaller than Mars, yet it maintains a denser atmosphere than even Earth. Moons like Europa, a large watery moon of Jupiter, might have ideal conditions for subaquatic oceanic life. Isn't it paradoxical and intriguing? These typical examples are right here in our very own solar system, yet they don't remind us that the potential for life exists in many worlds of vastly different sizes. The size of Earth is not a special prerequisite for life to form. The second point worth mentioning is the so-called habitable zone. If we have a planet the size of Earth with an atmosphere, we need to place it in a favorable location around its parent star to have the necessary temperature for life to initiate. This also seems logical. However, the thing is, a planet much farther from its star can have a denser atmosphere, leading to moderate conditions. A planet with a lower albedo or specific cloud cover properties might be closer to its parent star and still have moderate conditions. Hot planets could thrive in their upper atmospheric layers, while cooler planets could harbor life beneath ice. The habitable zone is a fifth-place starting point, and science has progressed to a point where this simplistic definition is no longer useful. The third point is the ability of a sun-like star. The majority of stars in the universe are red dwarfs, low-mass stars that burn slowly and steadily, in contrast to only about 20% of stars that share the fate of the sun, burning for billions of years before becoming red giants and ending as planetary nebulae. Although red dwarfs mostly have a low mass and undergo very slow nuclear reactions, emitting little light, many planets orbiting them are locked by tidal forces. However, this doesn't mean these conditions impede the formation of life. There is a risk of cutting off unnecessary possibilities by limiting ourselves to our primary assumption. While it's more likely that life in red dwarf systems may be challenging, until we truly start conducting a census of the universe's population, measuring the atmospheric properties of all available planets, we cannot make a comprehensive conclusion that life in these systems doesn't exist at all. The fourth point is that life regulates its own biosphere. This is another key question for which we don't have an exhaustive answer. Can a planet, initially uninhabited and considering only physical and chemical processes, transform and remain habitable during the early stages of simple life? We know Earth has many feedback mechanisms, and we also know that significant external changes might result in only minor changes within our biosphere. Does having simple, early forms of life hold the key to the development of stable, long-lasting life on a planet? After all, the conditions for its origin are more realistic and favorable. If this is the case, we cannot significantly understand what makes a planet potentially suitable for life until we gain a more complete understanding of this matter. The fifth point is the significance of heavy elements. The very first generation of stars consisted mostly of hydrogen and helium. In our solar system, about 2% of the total mass of all objects consists of heavier elements such as oxygen, carbon, nitrogen, and other essential life elements. Stars with a sufficient amount of heavy elements cannot form rocky planets, nor the simple molecules necessary for life. However, where do we draw this line? Can a solar system made up of half heavy elements be sufficient for life to form? And what if the percentage is 10, or even just 1? Or perhaps it could be as high as 500% in the opposite direction. Therefore, regardless of a specific threshold, we lack a clear understanding of whether we are a rarity in the universe or a typical outcome of probability theory. These are just some of the open questions that hinder our comprehension of a planet similar to Earth. An intriguing fact is that the universe plays with numbers. Consider our observations, for example, within the Milky Way. There are approximately 10 billion Earth-sized planets orbiting within the habitable zone of stars similar to our Sun in terms of temperature and mass. A significant portion of different systems have a comparable concentration of heavy elements to our solar system, indicating that a vast number of exoplanets could potentially be candidates for Earth-like conditions. However, there are also numerous exoplanets of a different type that do not meet these criteria. Such planets are far more abundant than those we naively describe as being similar to our own. The quest for Earth-like planets may lead us to overlook many planets in the galaxy where life may have already originated and begun to thrive. In order to discover something, a more unbiased approach would be to observe everything within our capability. Of course, it's easy to argue that Earth possesses all the conditions for life, which should at least allow us to consider the possibility that planets with similar conditions could also harbor life. So let's start by acknowledging the imperfections in our search for life on exoplanets. It's this kind of thinking that ensures we will obtain biased results in any search we conduct. But if, before the search even begins, we simply decide that life cannot exist around red dwarfs, that exoplanets or moons of incorrect sizes or at incorrect distances from their stars will never form life, or that stars with insufficient heavy elements cannot support life-bearing planets, we risk not only overlooking numerous cases of life in the universe, but also the overwhelming majority of habitable planets. The thing is, nearly 80% of the stars in the galaxy are low-mass stars, and there may well be more worlds the size of Mars or Liverpool, smaller than Earth, orbiting these stars than Earth-sized worlds. There's probably a multitude of atmospheric conditions that can permit life at various orbital distances. There might even be more exomoons of significant size around gas-rich massive exoplanets than Earth-sized exoplanets. So how tempting it is to assume that if we have one successful example like Earth, we should seek examples that mimic that known success. However, this is an incorrect scientific approach. The correct approach is to seek as many plausible worlds as possible that could include these conditions, not limiting ourselves to only Earth-like conditions. It's entirely possible that most planets with conditions similar to Earth's are actually inhospitable to life. Meanwhile, many planets with conditions different from ours may be even more suitable for life. Until precise studies reveal the answer, presuming that Earth 2.0 has a precise scientific basis is speculative at best. The story of how the universe became what we see today, from the Big Bang to the vast space filled with galaxies, stars, planets, and life, unites us all. From the perspective of inhabitants of planet Earth, 2/3 of cosmic history passed before the appearance of the Sun and Earth. However, life emerged on our world as far back as we can peer into the past through measurements. It may have appeared even 4.4 billion years ago. This makes us wonder, did life arise in the universe earlier than on our planet? How long ago might it have emerged? To be more precise, how soon after the Big Bang could enough heavy elements accumulate to form planets and possibly life? The answer to this question takes us further into the past than we could ever imagine. Graphite deposits have been discovered in zirconium, which is the oldest evidence of carbon-based life on Earth. The amount of carbon-12 found in these deposits dates the emergence of life on Earth to over 4 billion years ago. Of course, we cannot travel back to the very beginning of the universe, because after the Big Bang, there were not only no stars or galaxies, there were not even any atoms. Everything takes time to come into existence, and the universe, after giving birth to matter and antimatter, started from a fairly homogeneous state. The densest regions comprised only a small fraction, possibly as small as 0.3%, denser than the average. This means it would take an enormous amount of time for gravitational collapse to work on creating, for example, planets that are much denser than the average density of the universe. Yet, the universe had enough time for all of this to come into existence. If we look at the standard timeline of the universe's history, Earth appeared only after 9.2 billion years after the Big Bang, but many of the steps necessary for creating a world like ours happened very early on, just after 1 second. Antimatter annihilated with the majority of matter, leaving a small amount of protons, neutrons, and electrons. A sea of neutrinos formed, and after about 3 to 4 minutes, protons and neutrons combined to form neutral atomic nuclei, but most of these were isotopes of hydrogen and helium. Only when the universe cooled down to a certain temperature, which took approximately 380,000 years, did electrons join these nuclei, forming neutral atoms. However, even with these fundamental ingredients, life and rocky planets were still impossible because cooling the universe meant that atomic nuclei formed, followed by neutral atoms. Yet, practically all of these atoms were hydrogen and helium. Only much later did the heavy elements necessary for the formation of rocky planets and life begin to form. But gravitational collapse is a reality. Given enough time, it will change the face of the universe. At first, it progresses very slowly, but it gains momentum as regions of space become denser. The denser the region becomes, the better it is at attracting more and more matter, and the areas that start with the highest density grow faster than others. Our simulations show that the very first stars should have formed approximately 50 to 100 years after the Big Bang. These stars should have consisted solely of hydrogen and helium and could grow to quite large masses, hundreds or even thousands of times the mass of the Sun. When such a massive star forms, it dies within 1 to 2 million years, but in the moment of its death, something remarkable happens, all thanks to its life. All stars synthesize helium from hydrogen in their cores, but the most massive ones not only synthesize carbon from helium, they also progress to oxygen, neon, magnesium, silicon, sulfur, and so on, following the periodic table of elements until they reach iron, nickel, and cobalt. After this, there's nowhere else to go, and the core collapses. This triggers a supernova explosion. These explosions eject a vast amount of heavy elements into the universe, giving rise to new generations of stars and enriching the interstellar space. The increase in the proportion of heavy elements signifies an increase in the number of rocky planets with high density and the quantity of elements necessary for life as we know it. We don't need the average stellar system in the universe to resemble our solar system. We only need a few generations of stars to live and die in the densest regions of space to replicate conditions suitable for the emergence of rocky planets and organic molecules. For instance, in the remnants of a supernova, there exists a slowly rotating neutron star, formerly a massive star that reached the end of its life. Although supernovae can send the synthesized heavy elements back into the universe, it's the subsequent mergers of neutron stars that create most of the heaviest elements. By the time the universe reaches just 1 billion years old, the most distant objects are abundant in heavy elements, as confirmed by our measurements. There is a significant amount of carbon, as much as in our solar system, and other heavy elements accumulate even faster than carbon. It may take more time to achieve a high concentration because carbon primarily emerges in stars that do not become supernovae themselves. However, carbon is not essential for rocky planets, and other heavy elements also start to accumulate more rapidly. Possibly within several 100 million years after the ignition of the first stars, around 300 to 500 million years after the Big Bang, the most enriched stars have already formed rocky planets. This is seen in the protoplanetary disks around young stars. Gaps in these disks indicate the presence of new planets. As soon as the disk has a sufficient amount of heavy elements, rocky planets can emerge within it. If carbon were not essential for life, similar processes could begin in different regions of the cosmos. However, for life similar to ours, carbon is crucial, which means that the appearance of life may need to wait much longer. Even though carbon atoms will appear in the mix, it will take approximately 1.5 billion years for there to be enough of it. This period is before the universe reaches 10% of its current age. However, it's not just the 5% required for the formation of rocky planets. It's interesting to consider that the universe has formed planets and all necessary ingredients in the right quantities for life to emerge, except for carbon. To create a sufficient amount of this essential ingredient for life, we must wait until the most massive sun-like stars live and die. You see the remnants of supernovae on the left and a planetary nebula on the right. Both of these mechanisms allow stars to return burnt heavy elements to interstellar space, utilizing them for the emergence of stars and planets in the next generation. Sun-like stars, after their death, leave behind planetary nebulae, which are the primary source of carbon in the universe. It takes more time for the production of carbon because stars that give rise to planetary nebulae have longer lifespans than those that perish in supernova. Extrapolating that back into the past, the most advanced forms of life that appeared on Earth in different epochs suggest an interesting exercise. It turns out that the increase in genome complexity follows a certain trend. If we go back to individual paired bases, The time frame suggests something more like 9 to 10 billion years, rather than the 12 to 13 billion years ago the Earth formed. This indicates that life could have emerged a billion years ago. However, in our cosmic region, it took several additional billion years to initiate. On this semi-logarithmic graph, the complexity of organisms, measured by the length of non-redundant DNA relative to the functionally non-redundant DNA, with respect to gene readability through paired nucleotides, linearly increases over time. We do not know this at the current moment. We do not know where the line between life and non-life is drawn. We also do not know if earthly life began here before other formed planets, or somewhere deep in interstellar space without any planets at all. Many amino acids not found in nature have been discovered in the Murchison meteorite, which fell to Earth in Australia in 1969. The fact that over 80 unique types of amino acids exist in a simple cosmic rock suggests that the ingredients for life, or even life itself, might have emerged through interactions on planets. It's intriguing. The elementary ingredients necessary for life appeared shortly after the formation of the first stars, and the most important ingredient is carbon. As the fourth most abundant element in the universe, carbon is the last ingredient to reach the necessary quantity for rocky planets. In some places, rocky planets appeared much earlier than life could have emerged, perhaps as soon as 500 million years after the Big Bang, or even earlier. However, once we have enough carbon, all the necessary steps for the emergence of organic molecules and the initiation of the direction towards life become inevitable. Whatever life processes led to the emergence of humanity, they might have begun when the universe was 10 times smaller than it is now. We can be certain that in our solar system, we are alone. The maximum possibility is the existence of some microbes. These would not be complex multicellular organisms. But where are the intelligent beings? If intelligent beings truly exist in the universe, their location is at least light years away from us. Two independent intelligent civilizations could coexist, excluding interstellar travel. If they followed a similar path as our life, the question arises, where are they? Perhaps we should start with the fact that to emerge, life must go through several stages, yet the ingredients for it are literally everywhere. Even if we limit ourselves to life chemically similar to ours, the universe is teeming with possibilities. Molecules capable of binding, including organic ones, are present both on planets and in space. This is the Omega Nebula, or the Messier 17 mission, an intensely active star-forming region, which explains its dusty and vivid appearance. Stars formed at different stages of cosmic evolution have different proportions of heavy elements. Although Earth formed over 9 billion years after the Big Bang, the universe didn't necessarily have to wait that long. Therefore, we'll categorize stars into 3 population types. The first population type includes Sun-like stars, which consist of 1 to 2% heavier elements than hydrogen and helium. They are composed of processed material, and their planetary systems have gas giants and rocky planets suitable for life. The second population type consists of older, ancient stars with only 0.1% of the heavy elements found in the Sun. Most of their worlds are gaseous and rarefied. They are too primitive and contain too few heavy elements for life to emerge. The third population type includes the earliest stars in the universe, which should be almost entirely free of heavy elements. The study of the earliest galaxies indicates that they are mainly composed of stars from the second population type. However, closer to us, there is a mix of young and old stars, rich and poor in metals. In star distances, the scale is accurate in this illustration, but if the picture were to scale, even the largest stars would be smaller than 1/1,000,000th of a pixel. One of the most important lessons for astronomers came from the Kepler mission when examining the Kepler 4444 system. This first population type star has planets, but they are much older than our Earth. Our planet is only 4.5 billion years old, while the Kepler 444 system is 11.2 billion years old. This means the universe could have formed Earth-like worlds very early, at least 7 billion years before Earth appeared. Considering this possibility and the fact that regions like the center of our galaxy got enriched with metals faster and more significantly than our surroundings, it's quite possible that there are places in the universe, maybe even in our Milky Way, more conducive to the emergence of intelligent life than the Sun-Earth system. Given all that we know about the positioning of stars well suited for the birth of life, let's consider 5 main possibilities. This is the imagination of an artist regarding the TRAPPIST system, with its planets reflecting light from their surfaces. The potential presence of water on each of these worlds is depicted through seas, ponds, and vapor. However, it's unknown if any of these worlds have an atmosphere or if their parent star blew it away. One thing is clear. Potentially habitable worlds are located close to each other at a distance of only 1 million kilometers. In the early days of the solar system, it's likely that Venus, Earth, and Mars, and perhaps even Theia, a hypothetical planet that collided with Earth, had conditions equally suitable for life. Their atmospheres were filled with life-building ingredients, and there was liquid water on their surfaces. Venus and Mars at distances close to Earth's mark, a trajectory that spanned tens of millions of kilometers. However, around a Class M star, a red dwarf, planets could be separated by distances much smaller, as seen in systems like TRAPPIST-1. Potential habitable worlds could be as close as 1 million kilometers apart. Twin moons or planets orbiting a giant world, or a binary planet, could be even closer to each other. If life successfully emerged under certain conditions, why not have it arise twice, almost in the same place? This is a globular cluster, Omega Centauri, captured using a powerful telescope. Globular clusters are massive collections of hundreds of thousands of stars, forming a spherical shape with a diameter of a few tens of light years. In the outer edges, the typical star-to-star distance is about a light year, but in the denser inner regions of these star clusters, stars can be as close as the Sun and the Kuiper Belt. Orbits in these star systems must remain stable, even in such crowded surroundings. Considering what we know about globular clusters, which appeared much earlier than the Kepler 4444 system, there should be promising candidates for life and habitability within a few hundred astronomical units. Although this distance changes over time due to star motion, you could call this an incredibly close encounter of two civilizations. This high-resolution image operates very close to the infrared range. Such pictures allowed us to discover 3 superstar clusters in the galactic center. Since long-wave light near infrared penetrates the dense dust between Earth and the galactic center, we could observe these superstar clusters. This cluster is from the central parsec, and all stars in these clusters, as well as the galactic center, are quite young. The closer you get to the galactic center, the denser the stars are. In a few light years from the center, star density is extremely high, much greater than the center of a globular cluster. In a sense, the galactic center is an even denser environment with massive black holes and extremely massive stars and clusters forming. While globular clusters lack these, there is a problem with those stars in the sense that we see them in the Milky Way's core. They are relatively young, possibly due to high variability in their local environment. Stars rarely survive there for even 1 billion years, despite the high density. In this area, stars come in different sizes, colors, and masses, including many bright blue stars, which are dozens or even hundreds of times more massive than the Sun. This is evident in the scattered star cluster NGC 3766. So, let's consider the existence of a civilization in a densely packed star cluster, or a spiral arm. Spiral arms are rich in unusual regions of the galaxy, where young stars are more likely to form from these epochs. Star clusters often contain thousands of stars within a region just a few light years in size. However, stars don't remain in such a configuration for very long. A typical open star cluster disperses in just a few million years, and only a small fraction of them survive for billions of years. Stars constantly enter and exit spiral arms, including our Sun. In summary, while the typical distances between stars within a cluster may be around 1 light year, they are unlikely candidates as the cradle of life. This logarithmic diagram displays distances, showing the Voyager spacecraft, our solar system, and the nearest star. So, let's consider the latest idea that everything is distributed in interstellar space. In other cases, stars end up in the same situation we observe, distances between them being on the order of a few light years. Approaching the center of the galaxy, we can reduce this distance to what is encountered in open clusters, approximately 1 light year. But if we get too close, we face the problems we see in the galactic center: mergers, interactions, and other catastrophic events that are more likely to interfere. To maintain a stable environment, we can reduce the distance, but the typical interstellar space is not suitable for this. If we adjust for close encounters, the best approach would be to wait until another star passes close to the initial one. With a typical star, this happens approximately once every million years. This graph represents the probability of a star passing at a specific distance from the Sun, with both axes being logarithmic. While we don't expect intelligent extraterrestrial life to be a frequent phenomenon in the universe, as common as planets and stars, every world that meets the necessary conditions represents a chance. Each time you get a chance, you gain an opportunity for success, with a finite probability. Each of these possibilities may turn out to be reality, but until we venture there and see what is there and what isn't, it is essential to objectively assess what kind of extraterrestrial intelligence the universe may provide us. The truth is somewhere out there, but it's important to understand that if we were extremely lucky, it could be much closer than we dare to imagine today. What was before the Big Bang, from which our video now starts, you can easily remember by simply rewinding a bit, even from what your morning or this week began with. Though it may be a bit more challenging for some here, we are so accustomed to everything having a beginning that subconsciously we assume it for everything. However, what about something so old, even ancient, that its beginning cannot be found so easily? We've all heard about the Big Bang, but what preceded that event remains a mystery and nothing more than hypotheses. Despite the fact that the Big Bang theory is one of the most popular ones today, understanding it is not so simple. Moreover, it is crucial to remember that it is primarily a hypothesis, and we must consider the inaccuracies that scientists still need to eliminate with new astronomical observations and research. However, physicists have enough independent cross-data that makes the Big Bang theory the main starting point of modern cosmology. Everything around us is a direct consequence of an event that happened 14 billion years ago. According to the theory, space, time, matter, and energy were all confined in a fiery ball called the Big Bang. It expanded, and from its cooling debris, galaxies formed, including our Milky Way, one among approximately 2 trillion. The idea that the universe emerged from nothing was so insane that scientists were skeptical for a long time. However, existing evidence was convincing enough. Galaxies are moving apart like cosmic fragments, and the heat of the Big Bang still surrounds us in the form of cooled cosmic microwave background radiation discovered by radio astronomers in 1965. Today, scientists assume that all processes after the Big Bang were driven by the gradual cooling and thinning of the universe. As we know, temperature is a measure of particle motion, and as the temperature dropped, particles slowed down. The slower the particles move, the easier it is for them to come together. As the universe cooled down, initially flying quarks could merge into protons and neutrons and other hadrons and leptons. Then, the particles that had been obtained, continuing to slow down, began to form the first nuclei of familiar atoms, and so on. However, precisely what the universe was like during the Big Bang cannot be said with certainty. We can only assert that it was incredibly dense, and this changed over time. Everything we observe around us was incredibly tightly packed into a very small space in the beginning. But how can it be both infinite and at the same time so small? When people read about the theory, they might imagine that the universe was first smaller than an atom, then the size of a football, and so it expanded over 14 billion years. However, this analogy assumes that space initially had boundaries and an edge, but nothing suggests that the universe was not infinite even at the time of the Big Bang. Before that, it was smaller, and the object that occupied a square meter of space has now expanded to billions of light years. But even at the very beginning, the universe had no boundaries. Here's how it's explained by Professor Uriam Rocknes, a theoretical physicist at the University of Oslo. The entire observable universe comes from a tiny region that can be called a point, but nearby regions also expanded, and so did the next ones. Some of these regions are now so far away that we cannot observe them. If we think of the Big Bang as an explosion, it might seem like it started from a specific point at the center. However, when it comes to the birth of the universe, almost all galaxies are moving away from Earth in all directions. Therefore, Earth was never and will never be the center of the universe. Any observer on any other planet will also see galaxies moving away from them. In other words, the universe is expanding everywhere simultaneously. According to the inflationary model, the universe shortly after its birth experienced a very short period of exponential expansion, doubling its linear dimensions many times over. Scientists believe that this process began around the time of the strong nuclear force separation. This expansion, popularly known as cosmic inflation, was extremely brief, lasting only about 30 seconds. However, it increased the size of the universe by at least 10 to the 30, a billion times, possibly even more. But what if we want to look even further back in time, before the Big Bang? The main answer comes down to the fact that before the Big Bang, there was nothing at all. It means that the universe originated from nothingness, which is impossible even to imagine. When and why such a thing could have happened remains beyond comprehension. However, scientists insist on their position. Among them is the renowned theoretical physicist Stephen Hawking from England, who says that they didn't just imagine that the universe came from nothing. They arrived at this conclusion through rigorous mathematical calculations in which no one has found any errors. At some point in this mysterious nothingness, there might not have been familiar forms of matter, but it was not entirely empty, and certain processes might have been occurring that could give rise to small explosions. Ultimately, the Big Bang happened. To find evidence of this hypothesis, researchers try to create something similar to nothingness. They build special chambers from which they remove particles of matter and lower the temperature, almost reaching the coldness of space. Surprisingly, the resulting nothingness turns out to be something that can be studied in various ways. Here, we can think of vacuum energy and zero-point energy, but that delves into quantum mechanics, which would require much more time to explain. Still, many people disagree with the idea that the universe originated from nothing. Opponents of this hypothesis answer the question of what was before the Big Bang in various ways. Even though we know that the universe existed before the Big Bang, there is still very little that we can say about the nature of this ancestor of our universe. However, it can be assumed that something in its history led to a Big Bang, giving rise to our universe. Of course, there are other opinions. Perhaps before the Big Bang, there existed a universe similar to ours, or maybe entirely different. It is also possible to speculate that before our universe, there were at least two other universes whose collision led to the Big Bang. One can even imagine that the universe exists eternally, and in its history, Big Bangs alternate with big collapses. Such explosions could occur if the expansion of the universe changed to contraction. Finally, it can be assumed, and many agree, that at the initial moment of our universe's history, an incredible event occurred. The newborn universe rapidly expanded and inflated to enormous proportions, giving rise to bubbles in which different universes grew one after another. This way, a large universe emerged, also known as the mega-universe or multiverse. If this is true, just as our galaxy is one of billions of galaxies known to us today, our universe is one of many completely unknown other universes. But the most interesting, in our opinion, is the conformal cyclic cosmological model, abbreviated as CCC. According to this theory, the life of the universe consists of epochs, and each epoch's exponential expansion ends with a Big Bang, becoming a precursor for the next epoch. What would happen if one squeezes the distant future in the mathematical model of the universe, representing infinity as a finite boundary? What if the singularity of the Big Bang is stretched to the same smooth, finite initial boundary? According to the model, the universe goes through infinite cycles, where in each preceding cycle, the time in the future tends towards infinity, which becomes the singularity of the next cycle. It is assumed that the masses of all particles in the universe constantly and steadily decrease to zero over time, thereby increasing the energy. Additionally, an interesting assumption is that supermassive black holes, which are now detected at the centers of many galaxies, are relics inherited from past universes into our own. Professor Penrose's theory is fascinating, and we highly recommend exploring it. The cyclic theory exists in several versions, just like the inflation theory, and according to Professor Paul Stanford, the differences between them are purely technical and only interesting to specialists. The general concept remains unchanged. First of all, in our theory, there is no moment of the world's beginning, no singularity. There are periodic phases of intense birth of matter and radiation, each of which, if desired, can be called a Big Bang. However, each of these phases signifies not the emergence of a new universe, but merely a transition from one cycle to another. Space and time exist before and after each of these cataclysms, so it is entirely reasonable to ask about the state of affairs 10 billion years before the last Big Bang, from which the history of the universe is counted. The second key difference is the nature and role of dark energy. The inflationary cosmology did not predict the transition from decelerating expansion of the universe to accelerating expansion. However, when astrophysicists observed distant supernova flashes, standard cosmology didn't know what to make of the paradoxical results. The hypothesis of dark energy was proposed to reconcile these observations with the theory. Our approach is more internally consistent since dark energy is present from the beginning, facilitating the alternation of cosmic cycles. Nevertheless, as both Paul and Steinhardt note, cyclic theory has its weaknesses, particularly in explaining the collision and balance of parallel branes, i.e. lower dimensional spaces, from M-theory strings that occur at the beginning of each cycle. Other aspects of cyclic theory are better developed, but there are still many uncertainties to resolve. In conclusion, let's recall the following. Because events preceding the Big Bang have no consequences for observations, they can be excluded from the theory, and we can consider that time began with the Big Bang, as Hawking asserted. However, scientists still harbor hope of learning what existed before the beginning of time. Perhaps it was something grand or very dense, something that transitioned to us from another universe. There are more questions than answers, and for now, humanity is in search, and maybe someone among you will be able to tell the world what happened before the Big Bang. Have you ever wondered how our planet, our sun, and our galaxy came to be? Until recently, the universe was considered eternal, and its existence didn't trouble scientists. Albert Einstein even assumed the universe's eternity in his hypotheses and adjusted the equations of the theory of relativity accordingly. However, with the acceptance of the concept of the Big Bang, everything changed. Experts show that we live in the expanding and cooling remnants of a cosmic lump of matter. But what caused this initial explosion, and what preceded it? Did anything precede it at all? These questions are undoubtedly within the scope of science, but every attempt to answer them faces seemingly insurmountable obstacles, the infamous singularity, an infinitely small and dense point in which the entire universe, all the physics of the world, constants, matter, space, and time were compressed. Then, or during this event, the Big Bang happened, and everything listed above came into being. Nowadays, physicists have discovered the cosmic microwave background and started contemplating the very beginning. It's all a bit tangled, isn't it? The question remains, what was the problem with the existence of the cosmic singularity? It is one of the most serious problems in physical cosmology. The issue is that any information we have about what happened after the singularity can't provide us with any insight into what happened before it. Even now, so-called new physics leads us to the realization that our knowledge of the universe is still in its very early stages. Thus, at this moment, we can only talk about what we are capable of seeing with our eyes or through mathematical models on paper. One of the most frequently asked questions is, where exactly did the Big Bang occur? If there was an explosion, there must have been an epicenter. However, the reality is that our universe has no center. It is more accurate to imagine that the Big Bang occurred simultaneously everywhere in all points of the universe. Today, scientists assume that all processes after the Big Bang were influenced by the gradual cooling and decreasing density of the universe. As we know, temperature is a measure of particle movement, and as the temperature dropped, particles slowed down. Slower moving particles made it easier for them to interact with one another. During the universe's cooling, individual flying quarks merged to form protons, neutrons, and other hadrons and leptons. Then, these particles, continuing to slow down, began to form the first nuclei of familiar atoms. This period of the formation of the first atoms in the universe is called primordial nucleosynthesis, which lasted about 20 minutes after the Big Bang. During this period, the entire universe was heated to the state that we observe today inside stars. In this period, hydrogen and helium nuclei primarily formed in a ratio of 3:1, and these proportions of hydrogen and helium remain the two most abundant elements in the universe to this day. After the first nucleosynthesis, new atomic nuclei were hardly formed anymore, and the universe still remained hot, with matter existing in a plasma state. Electrons flew independently from nuclei, making the universe opaque to light. Photons constantly collided with electrons and couldn't travel straight, as if they were trapped in a mirrored labyrinth. This is why, by the way, you cannot see them through a daylight lamp or through our sun, which are also made of plasma and are therefore non-transparent. The universe continued to cool, and after about 300,000 years after the Big Bang, the temperature dropped sufficiently for electrons to join atomic nuclei. As a result, the universe became transparent. This moment is called recombination. The photons that filled everything around were no longer obstructed by electrons and could travel straight, instantly in all directions. Actually, these photons released at the moment of recombination are what we see today as the relic radiation of the cosmic microwave background. Next, the formation of the first stars occurred. It is assumed that these were very massive stars with a short lifespan that did not survive to our times. The first quasars, galaxies, and galaxy clusters and superclusters were formed. Subsequently, the formation of the interstellar cloud, which gave rise to our solar system, gradually occurred. Around the young sun, a gas-dust cloud formed. It should be noted that this disk was a remnant of the cloud from which the sun itself emerged in its early stages. This cloud gained rotation, which led to the formation of a rotating, flattened disk instead of a spherical one. At the beginning, the disk was 98 to 99% composed of hydrogen and helium, and the remaining elements were present in negligible amounts. However, it is precisely with their presence that the origin of planets is associated today. As the cloud cooled, refractory substances such as iron, silicon, titanium, nickel, their compounds, and others began to condense into dust particles. Condensation means transitioning from a gaseous state to a solid or liquid one. In the planetary cloud, there were no suitable conditions for most substances to exist in a liquid state, so gases heavier than helium and hydrogen immediately formed solid particles, bypassing the liquid phase. An example of this behavior can be seen with water vapor on Mars. Due to the relatively large mass of dust particles, they tended to gain more stable movement, moving toward the center of the disk. Gradually, a thin dusty disk formed inside the thick gas-dust cloud. With cooling, the number and size of dust particles increased, and the density of the dust disk increased. The rest of the initial disk became increasingly sparse. Eventually, the dust disk became many times thinner than its diameter. The composition of this dust disk was different in its different parts and depended on the distance from the sun. The inner regions, heated by the central star, cooled down, and more substances could form solid particles. For example, water vapor could transition into ice, probably somewhere around Jupiter's orbit and further away from the sun. At the same time, the solar wind blew lightweight gas molecules from the inner parts of the solar system faster than from the outer parts. As a result, gas almost left the regions close to the sun. The gradual cooling of the cloud facilitated the formation of countless compounds, mostly entering growing dust particles. According to the laws of physics, gases were more willing to condense on existing dust grains and less eager to form new ones. By the time the formation of the thin dust disk was completed, its density was tens of times higher than the surrounding gas density. The sizes of solid particles reached several centimeters, and the disk became gravitationally unstable. Random compressions in the disk did not dissipate, but on the contrary, kept recurring. This process culminated in the formation of millions of bodies several kilometers in size, which became the embryos of planets. They were named planetesimals. The composition of these planetesimals varied according to temperature conditions and the initial disk density, which, as we mentioned, depended on the distance from the Sun. During the next several 100 million years, the largest planetesimals grew, accompanied by the destruction of smaller ones. The small planetesimals were also ejected from the solar system due to the gravitational influence of the massive planets. The fastest growth was observed for Jupiter, as it was situated in an area where icy water particles had already formed. These icy particles contributed to Jupiter's rapid initial growth. Another important factor that gave Jupiter an advantage over other giant planets was its closer proximity to the Sun, where the dust disk's density was higher. The embryos of Saturn, Uranus, and Neptune lagged in growth compared to Jupiter due to the lower density of the disk in their formation regions. Jupiter managed to accrete a vast amount of gas while it was not yet swept away by the solar wind. Today, we see that Jupiter is the most massive planet among all the others combined in the terrestrial group. Though they formed in the densest regions close to the Sun, they couldn't become the most massive planets in the solar system due to high temperatures and dense solar wind streams. Solid particles formed with less enthusiasm, and heavy substances like iron and silicon were in the minority in the initial cloud. As a result, the solar system got small planets near the Sun, mainly consisting of silicon, iron, and their compounds. Among these planets, only Venus and Earth have sufficient mass to retain an atmosphere, which consists primarily of heavy gas molecules that move less rapidly. Therefore, the Moon and Mercury have almost no gaseous envelope, and Mars has already lost almost all of its atmosphere. During the formation of planets, smaller particles collided with each other. If such a collision occurred near a future planet, the colliding bodies could lose so much velocity that their orbit around the Sun became impossible. They were influenced by the massive planet's gravitational pull and became involved in its rotation. This way, rotating swarms of particles formed around large planets, a fate resembling that of the dusty disk. Soon, satellites began to rotate around planets, following the galaxy's perception of time. Another hypothesis states that planets were never molten spheres. According to this view, they originated from the gas and dust nebula surrounding the Sun, gradually condensing into a gas-dust disk, which eventually fragmented into separate parts. Some of these condensations grew to the size of planets. For example, our Earth formed from its embryo in approximately 100 million years. During that time, enormous meteorites falling on it heated its depths and left numerous craters on its surface. Later, the air and water erased most of the craters on Earth's surface. However, on other celestial bodies where these essential components didn't arise, such as Mercury or Mars, the craters remained intact. Moreover, the study of planets beyond our solar system revealed discrepancies that raised doubts about the hot disk hypothesis. Some of these inconsistencies were related to the class of planets known as hot Jupiters, which have orbits close to their stars with periods of a few days. Astronomers made adjustments to the hypothesis to address these questions, but it didn't solve all the problems. Thus, for now, we have to be content with theories that, while not complete, can partly explain the origin of everything related to the surrounding space. Perhaps a new physics will offer the world of scientists who can explain ancient processes in a new light. Earth is one of billions of planets located in the Milky Way. Once upon a time on our planet, there was no hint of life. However, thanks to thousands of factors and various random circumstances, life emerged on Earth. Over time, evolution progressed, and approximately 200,000 years ago, intelligent humans appeared, and at some point you were born. Interestingly, at some point, your parents were once small children, and at that time, your existence was not even a part of the plan. You began to grow, gradually getting older, but sooner or later, death awaits all of us. And any other galaxy is no different from the algorithm of human life. Galaxies have also died, including our Milky Way. So let's explore what kind of death awaits the Milky Way. Can it end its existence before its natural lifespan? And most importantly, what factors can influence this? Let's exclude the overused topic of collisions with the Andromeda Galaxy. Let's start by acknowledging that when the Milky Way galaxy was extremely young, it was overly active, much like when you're 14 or 15 years old, full of energy and ambitions. The galaxy produced new stars with significant intensity compared to today. As it aged, the galaxy's power diminished and star birth became less frequent. Determining the exact age of the galaxy requires knowledge of its color. It's not a secret that red galaxies tend to be older, while blue galaxies are younger. However, living on Earth with limited capabilities, it is not easy to precisely determine the Milky Way's age, so scientists rely on infrared light, which is not visible to us, but can be detected with specialized equipment. When this light passes through gas or dust, it becomes detectable. About 20 years ago, scientists believed the Milky Way was a young galaxy. However, modern research conducted in the last decade has led to a grim conclusion. The intensity of star formation in the Milky Way has been actively decreasing, although there are still large clusters of gas that could form new stars. These circumstances have left scientists puzzled about the actual fate of our galaxy. Researchers studying the life cycle of the Milky Way first seek to understand how a galaxy dies. To do this, they must eliminate various cold gases that affect star formation. Several circumstances could lead to this, such as the gas being expelled from the galaxy, no longer remaining cold, or being theoretically completely used up. To gain insights into the current state of the Milky Way, scientists find it easier to compare it with neighboring galaxies, like the one called Hot Dog, which is one of the brightest known galaxies with over 300 trillion stars. However, the intense brightness of Hot Dog is not solely due to stars. It is possible that a powerful quasar resides at its center. A quasar is an event closely associated with a black hole, and it serves as a source of light and heat. For this reason, it is quite possible that the quasar heats the gas responsible for star formation, leading to a significant decrease in the intensity of star formation in the Hot Dog galaxy, almost to zero. This leads to an interesting conclusion. Could a similar scenario be happening in our Milky Way galaxy? Just a couple of years ago, scientists came to the conclusion that one of the reasons for our galaxy's impending demise could be a supermassive black hole. This scenario would be similar to that of the Hot Dog galaxy. Currently, our Milky Way is surrounded by a large expelled gas cloud, and it is hypothesized that this gas formed due to the activity of the Sagittarius A black hole, which attracted an enormous amount of matter about 6 million years ago. The black hole heated up to such an extent that a sort of colossal gas explosion occurred, a galactic catastrophe of sorts. However, the Earth is located far from the Sagittarius A stray, especially in the outer part of the galaxy, so we were not directly affected by this galactic event. This theory suggests that the black hole is gradually affecting and potentially killing the Milky Way, making it a kind of galactic ulcer. Nevertheless, this theory has some significant gaps and inconsistencies. The explosion of Sagittarius A star occurred too late, and the Sagittarius A was active about 6 million years ago, which in galactic terms is relatively recent and may not have significantly impacted the intensity of new star formation. Therefore, besides the black hole, there must be another cause for the decline in star formation in the Milky Way. Otherwise, we can roughly conclude that the black hole that could hinder active and intensive star formation in the Milky Way should have been active hundreds of millions of years ago, and hundreds of millions of years ago, the Sagittarius A star black hole was not active. Therefore, assuming that the black hole Sagittarius A star is related to the future death of the Milky Way is foolish and unsubstantiated. The possible cause of the Milky Way's slow death may lie outside the boundaries of the Milky Way. If we examine the structure of our galaxy, it becomes quite messy. The Milky Way's disk consists of 3 main parts, a dense central core and spiral arms, one of which contains our solar system. The spiral arms should be flat, not curved. As for the edge of the Milky Way, there is an observable deformed region in the disk. The cause of this deformation is unknown, but interestingly, in 2016, scientists discovered 3 very ordinary stars that were no different from thousands of other stars. The fact remains that they recently left the galaxy at a speed of over 600,000 kilometers per hour. This led scientists to consider that the reason for the deformed disk might be found in these 3 stars that left the galaxy. However, this idea can easily be refuted because the galaxy's disk is too massive, and it is physically impossible for just 3 even large stars to deform it. So, the cause of the deformed Milky Way disk might be found in some dwarf galaxies. After all, our galaxy is enormous, and there are galaxies with as few as 100,000 or even 10,000 stars. It is entirely possible that such galaxies are numerous in the universe, but they are challenging to detect, especially close to the Milky Way. Usually, scientists observe large objects, and the reason for this is that the light from dwarf galaxies obscures the light from stars located in our Milky Way. There is only one type of stars, Cepheid stars, which allows for the detection of dwarf galaxies. This is because, firstly, Cepheid stars vary in brightness, and secondly, it is easier to measure the distance to them compared to other stars. Therefore, if scientists find Cepheid stars within the Milky Way, it would make it easier to detect a nearby dwarf galaxy, since there could be a star cluster present there. Remember those 3 ordinary stars that left our galaxy? Well, they are Cepheid stars. Hence, it is likely that a nearby dwarf galaxy is hidden beyond the edge of the Milky Way. By studying these 3 stars, scientists can easily learn about their past and bright future. Using Harvard's computer modeling based on the biography of the discovered Cepheid stars, scientists suggest that this dwarf galaxy broke through and deformed the plane of the Milky Way millions of years ago. In this event, tens of millions of stars must have inevitably collided, or at least that is what scientists believe. However, there could have been another scenario, as the distances in a galaxy are colossal and stars might simply have not encountered one another. In any case, the Milky Way suffered a cosmic traffic accident. Due to this collision, many stars came closer to each other, leading to gravitational interactions that significantly disrupted their movements and influenced their futures. For example, if you throw a stone into the water, you will see ripples spreading out in circles. A similar effect could have occurred with the dwarf galaxy after it passed through the Milky Way, and these ripples spread across tens of thousands of light-years throughout the galaxy. One such collision would not be enough to cause significant damage to the entire Milky Way. However, what if such a dwarf galaxy wasn't alone? Strangely enough, scientists believe that dwarf galaxies often collide with larger ones. Even in the present time, the Milky Way interacts with several other dwarf galaxies. For example, there's a dwarf galaxy from the constellation Canis Major, which is closer to us than we are to the core of the Milky Way. So not all the stars we see in the sky belong to our galaxy. So what happens when multiple dwarf galaxies gravitationally interact with a large galaxy? We already know what one dwarf galaxy can do, but when multiple dwarf galaxies are involved, they can even change the structure of the larger galaxies. If dwarf galaxies didn't influence our Milky Way, it probably wouldn't look the way we've observed it for thousands of years. The numerous interactions of dwarf galaxies with the Milky Way could have altered its shape, and gravitational effects might have created objects in the galactic center that pose a danger to the dwarf galaxies. One such object is the galactic bar, a long, thin structure where stars are located. However, the bar itself can be harmful to the galaxy, as it can draw gas into the center. The deficit of gas could disrupt the formation of new stars. In the core, the supermassive black hole absorbs gas, but without enough material, new stars cannot form, and the galaxy gradually dies. So, do dwarf galaxies really kill the Milky Way with the help of the galactic bar? It seems that, indeed, the fact is evident that due to the bar and the black hole near the core of the galaxy, there is no active star formation. But what could be the reason for the lack of active star formation far from the center, for example, in the ordinary spiral arms? Could it be that the Milky Way is destroying itself? Let's try to understand. The Milky Way galaxy has a diameter of about 100,000 light-years, but it wasn't always this large. Firstly, stars weren't born in it from the very beginning. Secondly, as we already know, our galaxy has merged with other smaller galaxies, and this process continues to the present day. When a smaller galaxy collides with a larger one, it gets fully absorbed, meaning that the Milky Way doesn't necessarily need to collide with others to replenish its gas. So, the most logical explanation might be that the Milky Way is self-destructing. Now let's look at other galaxies in the universe, but with a small reference point. The galaxies we see are billions of light-years away, meaning we are looking into the past and seeing them as they were billions of years ago. By comparing them with galaxies closer to us, we can track their entire evolution and the aging process based on this method. Using this approach, scientists analyzed around 300,000 galaxies and came to the conclusion that all dying galaxies, similar to the Milky Way, share one common characteristic: high mass. This means that galaxies have a mass limit. For example, spiral galaxies with masses up to trillions of solar masses actively form new stars, but once they exceed this threshold, they begin to die. So the high mass of the Milky Way could be the reason for its gradual demise. As galaxies age and increase in mass, they experience a decline in star formation, and the Milky Way might be following this pattern. This process is evident in other galaxies as well. Therefore, we can conclude that the Milky Way galaxy, throughout its entire history of existence, has accumulated such a high mass due to merging with dwarf galaxies that it is now gradually starting to die, or more precisely, it is already dying. However, it is worth noting that the halo of the Milky Way currently contains so much gas that the galaxy simply refuses to form stars from it. It's like a cosmic overeating. To weigh a galaxy, one only needs to measure the speed of stars. The faster the stars rotate around the galaxy, the heavier it is, as gravity cannot be disregarded. In other words, the more stars move, the stronger the force needed to keep them in their orbits, hence the higher the mass. Based on astronomical research by Australian and American institutes, scientists have calculated the mass of the Milky Way and concluded that it has surpassed that critical limit. Paradoxical as it may sound, the gravity of the Milky Way galaxy is killing it. It simply devours other dwarf galaxies. But can the demise of the Milky Way be avoided? After all, a collision with the Andromeda Galaxy is looming, but that's another story.